Good morning, everyone. I am Dhanasekaran, Assistant Professor, Department of ECE. Today, I am going to present you that advanced risk machine in the course name of embedded system. So, let's see. So, first, the contents are introduction and risk architecture, ARM design philosophy. Okay. So, first, what is ARM? ARM is a advanced risk machine. So ARM is especially designed for portable devices due to the low power consumption and for reasonable performance. It is a most licensed processor and widespread in the world. You know that it is a most licensed processor. Okay, it is first ARM processor developed at Akron Computers Limited 1983 to 1985 during this period, and ARM is a 32-bit reduced instruction set computer, that is a RISC instruction set architecture ISA developed by the ARM Holdings. So we have to know that what is a reduced instruction set computer. Okay, so it is executed by the single cycle execution. It is a low cost one, and we can easy to fix, and we can program simply. Okay, so these are comes under a reduced instruction set computer, and we have a pipeline processor execution in this, starting a second instruction before the first one is finished. That is while you compiling the program, the first instruction is executed, that is a second instruction started before the first one has finished. That is, so it has some 32-bit register, that is a large register bank, all of which can be used for any purpose to allow the load store architecture to operate efficiently. And one more advantage is the load store architecture, where the instruction that process the data operate only on RISCs and are separated from the instruction that access memory. And you know that it is a 32-bit processor, that is an instruction size with a few formats. That is a fixed 32-bit instruction size with few formats. And one more thing is hardwired instruction decode logic is there in the reduced instruction set computer. So next instruction set type is 2, that is a complex instruction set computer. So in this the clock rate is very uh, low in complex instruction set computer, and is cost is more compared to reduced instruction set computer. And it has a multi-cycle execution time, that is it takes multi-cycle for execution, rather reduced instruction takes only the single cycle for executing the instruction. And I intended to reduce the semantic gap. I tell you the next slide what is semantic gap. So the distance in the implementation times between the high level language construct and the machine instruction. The single instruction produced entries and exist. You know that variable length instruction sets many with many formats. So it has variable length instruction sets with many formats available, and complex sequence of operation over many clock cycles. And the next one is CISC were sold on the sophistication and the number of their addressing modes, data types, etc. So CISC based on the use of in the sophistication uses, and it was developed in the year of 1970s when computers had low main memory, so the processor were controlled by the faster ROM, and frequently used operation are drawn in the ROM's micromet sequences rather than having instruction full from the main memory. So here we can access memory through microcode sequences. See, that is a third one. Here instruction set type 3. So see, as I already told that the semantic gap. So what is semantic gap? Semantic gap is nothing but a distance between the programming language and the machine's code. That is a programmer to the hardware. The in between gap is a semantic gap. So when the programmer creates a programmer that's going to be run and that is going to be dumped in the hardware for better working. So in between we have the semantic gap. Okay, that is we expressed in the equation, that is execution time is equal to instruction count into the clocks per instruction into clock times. So execution time calculated with the instruction count, clocks per instruction and clock times. Okay, so IC is called instruction count and CPI is called clocks per instruction and CT is the clock times. So IC is the number of instruction and the CPI is the average number of clocks per one instruction execution, the time taken by the one instruction execution, and the CT is the clock time. And here you have to note that point CISC is a reducing IC, that is reducing instruction count, whereas in the RISC it is a reducing clocks per instruction and clocks uh, times. So it's reducing the clocks per instruction and clock timing. So here you can understand what is semantic gap. See, so programming language and the machine code. So in between the CISC reducing the clocks per instruction and the clock timing. Here the RISC reducing the instruction count. See, instruction type set type 4. Here you can easily understand the compiler processor. So in between we have the code generation. Here where the complexity arises. In CISC it emphasizes hardware complexity. So you can see the images that shows where the complexity arises. In the RISC, as we said already, it takes high clock rate and it is a low cost one. It creates the complexity in the compiler side. Okay, so it takes only the single cycle for the execution of one instruction. And these are the advantages of RISC architecture. And coming to the advantage, first advantage is a smaller die size. A simpler processor requires fewer transistor and less silicon area. The next one is a starter development time, that is a less design effort and therefore the low cost. So it takes only the we cannot put more effort to design RISC. We can easily design RISC and therefore the low cost. Okay, and high performance. Coming to the high performance, so it carried out the simple instruction for the executing fast, so that the high performance we can be acquired a high performance here. And coming to the disadvantage about the RISC architecture, here the poor code density compared with the sorry uh, yes, here the poor code density compared with the CISC and doesn't execute the 86 code. So these are the two disadvantages of RISC architecture. And coming to the history of ARM, founded in the November 1990s, span out of Akron Computers, and designed the ARM range RISC processor cores. As I already said, it's most licenses ARM core designed to the semiconductor partners who have fabricate and sell to their customers. The next one is ARM does not fabricate silicon itself. Also develop the technologies to assist with the designing of ARM architecture. Okay, so here we have the software tools, boards, debug hardware, application, etc. And software and software buses for the architecture, and peripherals, that is serial and parallel, like that. So ARM design philosophy overview. Here the simplicity is the key philosophy behind the ARM design. So we have the reduced power consumption, essentially future for the portable embedded system. So it is specially designed for the portable devices due to the low power consumption and reasonable performance. So such as mobile phones, personal digital assistants, PDS, you know that very well about the mobile phone. It is one of the application of embedded system. It is a very most example that is we can show the embedded system application as a mobile phone. And the next one is a small amount of silicon die area, that is a RISC machine with small instruction set, consequently a small gate count. And the next one is a low cost and low power consumption, as we have already discussed more on this. So the next one is a system on a chip, that is for a system on a chip solution, more area available for the specialized peripherals. So these are comes under the ARM design philosophy overview. And about coming to the hardware debug technology, here the software engineers, that is a firmware engineer, can examine the processor state while the processor is executing the code. These advantages comes under the ARM. So the engineer can examine the processor state, so while the processor in the executing mode. So and the next one is reducing development costs and time. So by using the ARM design philosophy, we can reduce the development cost and time in the hardware debug technology. And the ARM design philosophy, the next that the instruction set for the embedded system. So ARM instruction set differs from the pure RISC architecture for the embedded application. So first one is a variable cycle execution for the certain instruction, an inline parallel shifter, and we have a dump 16-bit instruction set, and conditional execution, and the next one is enhanced digital signal processing. So this is the ARM core based embedded system architecture. You can see that advanced high speed peripheral buses are available, and the main components are ARM processor, controller, bus, and peripherals. These are in the ARM architecture. So the main components are ARM processor, controller, bus, and peripherals. So this is system on a chip, a collection of all kind of components, that is a DSP, CPU, decoder, DSE, everything it's in the picture, memory. So like that everything are appropriately interconnected to perform the specified function and for end users. So this is a system on a chip. So you can see the picture, that is it has memory, DSP, DAC units, and embedded software, RTOS. So everything integrated in the chip. That is a complex IC that integrates a major functional elements of a complete end product into a single chip. So these are integrated in the single chips in the ARM. Okay. So thank you all for watching this video. Thank you.